A seesaw is a pretty amazing toy and a beautiful example of rotational motion. It rotates about its own center of mass, its own natural pivot, so that the only reason I need this physical pivot passing through it is to prevent the seesaw from falling. If I could turn off gravity, I wouldn't need that physical pivot to make the seesaw do exactly what it's doing. Well, there is gravity, so you need the central pivot, and the pivot also constrains the seesaw so it can't do rotations that we don't want. It can only do what you see it doing at the moment, although it can also do that in the other direction. The seesaw is balanced as well, meaning that it's experiencing no torque due to gravity. That's because the center of gravity of the seesaw is located right at the pivot as well, basically vertically in line with the pivot. In fact, it's on the pivot, and as a result, that the force of gravity produces no torque on the seesaw about its pivot. No torques. So the seesaw is turning according to Newton's first law of rotational motion. It's a rigid object that is not wobbling and it's not experiencing any external torques, so it rotates at constant angular velocity. Well, when you put riders on the seesaw, life can get more complicated, as we've seen. Those riders produce their own torques on the seesaw, and they move in various interesting ways. If they're not balanced, the seesaw undergoes angular acceleration in various ways, but once they are balanced, and again there's no gravitational torque on the seesaw and its riders, the seesaw is once again rotationally inertial. It turns according to Newton's first law of rotational motion. If they come out of balance and the seesaw undergoes angular acceleration, it does so according to Newton's second law of rotational motion. The angular acceleration of the seesaw is equal to the net torque acting on the seesaw divided by its rotational mass. And depending on where the riders sit on the seesaw, they can go from giving the seesaw a small rotational mass to giving it a large rotational mass. Lots of flexibility. As they're tipping back and forth, they're exerting torques on one another, these two riders, and that's according to Newton's third law of rotational motion. If the red rider exerts a torque on the purple rider has to exert an equal but oppositely directed torque back on the red rider every time. And as they tip up and down, they do work on each other. They transfer energy to each other with the help of the seesaw board. So there's really a lot going on here in the seesaw, and we'll use many of these same concepts later on as we continue to look at how things work.